Okay, welcome back, everyone. So I'm going to be running this second session, and this is the first of our two research update sections that I described to you previously. There's going to be some framing talks by the PIs, followed by a series of lightning talks from the researchers. The first session is going to be based on the first two themes: promoting return to forest cover and restoring natural carbon dynamics. So I thought I'd give you a little bit of advice, some tips on how to survive a BERA research update, because what's going to happen is there's going to be 15, 16 research talks in the next short period of time, and it's going to be a little bit overwhelming. So I would think of it like speed dating. People are going to stand up and they're going to give you a 2-minute elevator pitch, basically, about what they're doing, why they think it matters, maybe some preliminary results, or if they're later on in their project, they tell you what they found. So I sort of envisioned you noting either the names of the researchers or the project code as everyone stands up. And then you've got these handy dandy little black books, almost partly a little bit black books, where you can write down the researcher or their project number that you want to go speak to. And then when we break into the poster session, that's where you're going to find them. So they're all going to, when they're doing the elevator pitch section, you can see they're already starting to line up. Scott's going to give his overview, and then they're going to shuffle through. And then when they're done, they're going to go out and attend their posters, where you can go and interact with them. So hopefully, as they're speaking, you're making notes of the researchers that you then want to go speak to. That's my advice. Otherwise, it's just going to be a blur, and you're going to go out there, you're not going to sure who to talk to. So yeah, that's the way I would do it. Scott Nielsen, Dr. Scott Nielsen, the PI of the vegetation team, the lead of the vegetation team, will take over from here.
All right, thanks. So I'm going to give an overview of, for a few minutes, the vegetation work. It's just part of it, and we'll have lightning talks for each of the folks with their posters. So this theme is promoting a return to forest cover, basically the vegetation. Our strategic priorities, to remind you, are promoting return to forest cover, and to do that, our tactical deliverables are looking at growth, survival, abundance, and height of vegetation. And it's relative to what we've been talking about, either active or passive treatments, and a number of different strata or ecosites or disturbance histories. The variables that we're looking at are either like direct measures at field plots, include that growth, survival, abundance, height. But we also are interested in extrapolating or predicting those relationships to other places. So we develop statistical models with GIS and other variables to make those predictions elsewhere. Now I'm going to step back for just a minute and talk about restoration success. I think we started talking about this morning. Caribou, 65% disturbed, not numbers, lambda growth rate, vegetation, how high should it be, how dense should it be, what is a forest, what is not a forest. And if we think real broadly, we can think of restoration and targets as either being from a place or a time. In a place, you can have the same place or a different place. In the time, you can have the same time or different time. So a different time, different place would be like a historical reference model of something. Or the same place, but a different time is a historical model of what, let's say, that stand used to look like. Now, if we think of the same time, we can think of it as our contemporary remnants or contemporary sites. And in BERA, this gets really confusing, because in BERA, when we're doing the vegetation monitoring work, we're looking at the line itself and the disturbance. And we're often using the adjacent forest as like a reference or a control or a comparison. But of course, that forest is, let's say, 75 years old or 120 years old. And yet we're looking at what's the recovery on the line. So in reality, what really is our reference, what really is our target? it gets a bit confusing. In some instances, well, it's dynamic, it's succession. We're trying to promote trajectories of recovery, right? And in that instance, it's like, well, what shouldn't our reference or our comparison be maybe a different place that, maybe was recently burned or a clear cut or something undergoing natural regeneration processes? And these are some of the things we need to think about. And I'll just consider one of our strategic our measures, and that is height and these height targets. And even that gets pretty confusing. So, there's various rules like 70% cover of species capable of reaching 5 meters and 50% cover on either side of the line. And I'll just mention this, that, okay, 5 meters. And, is this one rule? I mean, if we think of the different ecosystems or different ecosites, here is some LiDAR data that I was processing for the BERA region, the whole BERA region, and divided it into different forest types: deciduous forest, mixed forest, conifer forest, pine forests, and then our peatland types, tree bog and tree fen. And there's going to be a wide variability. But if you take the median, and I should mention these are after removing all the footprints, the adjacency of the footprints, recent fires, clear cuts, everything else. So these are kind of like our reference ecosystems. And some ecosystems like the treed fen, well, the median is 4 meters. So as we know, like black spruce and tamarack and so on doesn't grow very well or very fast. And, I'm just pointing out that, a single rule is maybe going to be somewhat problematic for defining success. And it may vary by place. At the same time, we don't want to overcomplicate everything and say every place should be different. But I think we also need to think of, the possibility of having other targets or references that are site specific. And, all these things are going to be affected. I have this graph down below, just establishment, survival, growth, height, density dependence. That's going to influence all these different things. So one of the things I did, again, that same LiDAR data set, is I sampled like all over the landscape and looked at what the LiDAR heights were, again, outside of places that have been disturbed recently by anthropogenic processes. And I looked at, well, what's the, specifically for this example here, I looked at all places that had recorded fire history in the BERA landscape, the age of those sites and the environmental conditions of that place, and looked at, well, what's the height? What is the natural trajectory that we would typically see across this area? Well, it's going to be different. Jack pine sand is going to be different from an aspen forest versus, obviously, we saw the peatland, the treed peatlands are going to be very slow. So if we take different variables, let's say like time since fire we want for sure, because we want to know that trajectory. The climate moisture index, what's the heat and moisture of the region, mean annual temperature, a terrain wetness metric based on a DM, LiDAR DM, and percent sand. If it is an upland, we kind of say these upland sites that are, essentially sandy with jack pine forest versus not. And if you look at various interactions of those things and use quantile regression, so quantile regression, just as an example on the bottom there, if we take two simple factors, age of the stand and height of the stand. You can have a really old stand, or you think it was old based on the fire history and has no record of disturbance, but for whatever reason, there's windstorms, ice storms, something else, the height may be pretty low. But if you take like the 80th, 75th, or 90th quantile, that would be a stand that essentially has succeeded in height growth for that site under optimal conditions, if you want to think of it that way. So anyway, this map on the right is a combination of all those factors where I'm estimating the height of different stand ages, potential stand ages. So re-predicting back on the landscape what essentially like a site index is. So in this case, I'm showing age 40. What should the height be at 40 years since disturbance? And it's going to be quite variable. And it comes back to the point of what is our targets? What is our reference? What should we be using? In this case, just for one metric, height. And just pointing out that I think there are some opportunities to think through these issues we're talking about. So another thing here as well, that's like natural stand height. So places that have been disturbed since fire history is known. since 1931. And, you know, obviously we're going out and measuring the specific height recovery trajectories and densities and other things, the abundance of trees and so on. And these are just some graphs over on the right. Maybe the lower right's the most relevant, from Angelo and myself on his work, his PhD work. And let's just take the red dashed and the red line. So on the y-axis, that's tree height, and on the x-axis is age of line. That's actually not right. It's age since establishment. We didn't know the age of the line. So through Dendro, we knew the age of the tree on the line, but it could have taken X number of years before that tree was first established or recruited on the line. Now, hopefully with ABMI and other data sets trying to attribute line age, we can kind of fill that gap. But since establishment, we have these two curves. The red curve, solid curve, is in a jack pine site, what's the natural height recovery once a tree establishes? Not post-fire, just on a seismic line surrounded by trees on both sides of the seismic line. The dashed red line is post-fire. Of course, you get rapid regeneration post-fire, jack pines, serotinous cones, everything else. It's just gonna, you know, reboot that system, and it's gonna quickly grow. These are some of these height trajectories that we'd expect, either on the line, you know, maybe I'm giving you a reference over in the forest, plus what happens when you expect a natural recovery post-fire. So one of the key things, the last thing here before I start introducing the speakers is, you know, so ABMI has this, you know, lineal inventory of seismic lines. So on your left side is conventional 2D legacy seismic lines all over the place. And on the right side is the 3D low impact seismic line, generally within leases, obviously, of in situ plays. I think if you add it up, I think it's, I don't know, maybe Greg could correct me, 150,000 kilometers of seismic lines in this area. So these I attributed these lines relative to those eco sites. And what we're trying to do is also attribute, like, we have a series of locations where we've collected data. We use that information to try to generate statistical models to predict it everywhere. In the long term, remote sensing hopefully would fill in and directly measure the responses. And some responses will be very difficult to do, like composition of seedlings and, you know, even density or abundances, but at least maybe height, it'd be excellent. That's part of the reason I picked on height. Height hopefully is something that's achievable through remote sensing everywhere. But regardless of that, we could attribute each of these, until that happens, we can attribute each of these line segments to what we expect reference conditions to be, to what we expect recovery should be, and places we think natural recovery is probably happening anyway. Now, it's not going to be as accurate as remote sensing and you know, pre-restoration work to demonstrate, yeah, that line definitely has vegetation growth and so on, but probably point us in the right locations. So here's the 5 projects in this session. So the first one is going to be Colleen. And Colleen is going to talk about a small part of her overall PhD work on some work she did this summer on, you know, transitional swamp sites. But broadly speaking, she's kind of working across these areas of growth, abundance, and height, and kind of extending some of that modeling framework I was talking about by leveraging old, you know, existing data sets that we have gathered, as well as filling the gaps with more data that she's collecting. She'll talk about, you know, not that whole thing, but some early summer work that she's done. So Leonardo is going to talk about, you know, broadly speaking, his PhD work is on also modeling at landscape scales, what we expect different possible landscapes or systems or forest types or state and transitions to be, especially given things like climate change and changes in fire regimes and stuff like this. He's going to talk, however, that although that's his bigger project, he's going to talk about inside clear cuts, what's the implications of clear cuts and regeneration on the seismic lines. Either it kind of erases it completely, or maybe there's some legacy effects of maybe the way the seismic lines were created, even with silviculture, maybe it's not coming back quite as much as it is, you know, in the cut block. Well, maybe it is, maybe it just kind of reboots the system, and you don't have to worry about investing more restoration if it's going to be harvested anyway. Colette from the remote sensing group is going to talk about, there's a number of projects on this, and I already hinted at. So Mounding is the favorite silvicultural action for restoration, particularly in the peatlands. And Colette's going to talk about growth and survival of seedlings on mounds and off of mounds and that type of work. She has, I think, another project and another session she will also be talking about. Jennifer from the soils and hydrology work is similarly going to talk about the mounding and seedling growth, but also relative to the complexities related to hydrology and soils, and essentially, if we want to think of it as the microsite conditions. And then lastly, Spencer's looking at the question of browse subsidy. So, you know, if there's 150,000 kilometers of seismic lines, you know, we have this issue of white-tailed deer expanding in the boreal forest since World War II. To what degree does the early seral landscape further increase populations of things like deer or change their behaviors of where they go, i.e. seismic lines to browse on the winter browse that's there or not? So he'll ask that part of the question. So I think with that, we're going to quickly go through these lightning talks, and that will bring us to Colleen first.
Thanks, Scott. Yeah, so I'm Colleen Sudheimer. I'm a first-year PhD student with Scott, U of A. And yeah, like Scott said, I'll be presenting just like some preliminary stuff about the first project of my PhD, which is looking at passive recovery specifically. So yeah, awesome process diagram. So as part of the vegetation team, I'm concerned in how can we promote forest return in boreal ecosystems. So I use direct measurements of growth, abundance, and height of trees and shrubs within the line and then in adjacent forests to hopefully model those recovery trajectories. And for us, this is important because we can identify where recovery is happening, but we also want to know how long it's taking. So one of the few gaps we had in our existing data set was in these transitional sites. So transitional sites usually have upland and lowland forest types, such that our data from upland or lowlands probably is not great for modeling them. So that's basically what I did this summer. I sampled sites from Loch Labish to Fort McMurray, a lot of swamping, and we filled this gap now. So with the work that Angelo did in BERA phase 1, we have now over 460 sites across our study extent to build those models. So with that extensive data set, I'm going to incorporate multiple variables like Scott was mentioning to build spatial and linear models to predict growth, abundance, and height in order to approximate these recovery trajectories, so how things are changing over time. And then so this first part is just focusing on passive, but this summer we're also going to do target active lines. And the hope is that we can then do those prioritizations so we can compare these recovery trajectories and figure out where things are going to meet recovery targets so stakeholders can target their treatment efforts. So thanks. And if you want to learn more about what I learned in swamps, come see me at the poster session. Thank you.
Okay. Hi, everyone. My name is Leonardo Vigliani. I'm a first-year PhD student at the University of Alberta under the supervision of Dr. Scott Nielsen. And today I present my first project in the BERA vegetation team called Forest Harvesting Promotes Seismic Line Regeneration in Mesic Upland Forest. In the context of seismic line regeneration, understanding when the natural reforestation of the line occur without active restoration treatments is a priority. And we know that seismic line can occur together with other resource extraction, and one of them is forest harvesting. Forest harvesting usually provides several factors that promote the regeneration of early successional stands in the post-harvest area. And based on that, a key question is whether forest harvesting can erase seismic line without further restoration needs. For my first project, I studied the effect of cut blocks on the regeneration of seismic line in the Mesic Upland Forest. And after that, in the future, my research will focus more on other disturbances effects with specific attention on climate change. To answer my first question, this summer, I studied the tree regeneration in 15 Mesic Upland cut blocks from Fort McKay in the north to Loch Labish in the south. And I performed a regeneration survey in 2 plots in the mature forest and 2 plots in the cut blocks, counting all acceptable regenerating trees and shrub species. With this data, I compared the regeneration density inside and outside the line in the Mesic cut blocks, upland cut blocks, and mature forest. If you're interested in my research, please come to talk with me during the poster section. Thank you for your attention.
Hey, good morning, everyone. My name is Colette Chillian, and I'm part of the remote sensing team with Greg at the University of Calgary. And today I'm going to tell you about my master's research, which I completed in September. And my project investigates seedling growth rates on actively restored seismic lines. My project is situated in the strategic goal of promoting a return to forest cover. And specifically, I'm looking at how active restoration treatments influence seedling growth rates of black spruce and tamarack in poor and rich fens. So we know that fens are one of the most common wetland types in the boreal, and unfortunately, they also often show signs of arrested succession, where trees and other vegetation are not proceeding along regeneration trajectories as we might expect. And we know that there are several interacting factors that are linked to failure of tree establishment and growth on seismic lines. The heavy machinery that creates seismic lines crushes natural hummocks, and this eliminates suitable microsites for seedlings to establish and grow. The ground surface of seismic lines is often lower than surrounding undisturbed forest, and this predisposes seismic lines to high soil moisture content and potential flooding. So inverted mounding, which involves flipping vegetation onto itself to create a raised planting site, is meant to mimic natural microtopography and improve growing conditions for seedlings. So my project asks if restoration treatments, tree planting and mounding specifically, enhance seedling and sapling growth. To answer these questions, I measured seedling height and growth in Kirby and Lydia 1 on about 30 different seismic lines and assessed their growth between the treated and untreated lines using mixed models. So my project is useful for managers who want to understand how restoration treatments could be used to help trees reach canopy height more quickly. So I don't have time for my results now, but if you would like to find out more about seedling growth rates on actively restored seismic lines, come join me at my poster. Thank you.
Hello, my name is Jennifer Fleeser. I am a second year's master's student working with Dr. Maria Strack at the University of Waterloo. And my project is looking at the effects that mounding has on tree seedling survivability and growth on seismic lines specific to peatland. For a bit of context, we know that trees are not naturally regenerating at an effective rate on seismic lines, but the reasons behind this are very complex, and we don't have a perfect restoration solution. What we do know is that microtopography and hydrology play a large role in tree growth in peatlands. So one of our working hypotheses is that if we use planted mounding to positively change the microtopography and the hydrology of seismic lines, we can then promote the return to forest cover. My project examines 4 unique mounding treatments: rip and lift, hummock transfer, inline mounding, also called upright mounding, and inverse mounding, along with unmounded sections of seismic line and natural comparison sites. And my research variables are looking at height variables, at growth, at microsite conditions like mound elevation, soil moisture, and surrounding vegetation communities. In terms of connections to BERA, the study is focusing on the return to forest cover and its relationship to microtopographical change, looking at it from a soils perspective. So in this diagram, we can see connections to growth and survivability and ground vegetation at the microsite level. And I have connections to this, to our natural carbon dynamics process diagram, looking at microtopography, tree establishment, soil properties, soil water retention, and availability. So the overall goal of my project is to identify which out of all these characteristics is driving seedling growth. And by identifying these driving characteristics, we can plan more effective restoration solutions that help seismic lines revegetate faster. If you're interested in discussing my project and hearing my results, please come visit me at the poster session.
Good afternoon. Welcome to this lightning talk. I'm Spencer, And I'm working with BERA to study the connection between the kind and abundance of vegetation regenerating on seismic lines and observed increases in ungulate populations in the southern boreal forest. If you're looking for a helpful diagram of that, you'll find one on the side of your BERA mugs that were handed out at the door. So, never mind. Okay. White-tailed deer in particular have increased by 1,600% in northeastern Alberta over a span of 20 years. And when deer numbers go up, wolf numbers go up. And higher wolf numbers means increased incidental encounters with caribou. Caribou, with their low birth rate, struggle with that extra predation pressure and have rapidly declined in the region. And within the province as a whole, where they're listed as threatened. Okay, so, oh, I actually got too far ahead. Sorry. Okay. Oh yeah, so what's missing from this picture is an explanatory link between seismic lines and competitor ungulate populations, that is deer and moose. So could it be that these disturbances are producing a surplus of browse that is subsidizing ungulate populations? That is the browse subsidy hypothesis, and that is what I'm trying to test. Okay, so to do this, I'm going to visit 60 seismic lines and compare the availability of preferred browse on the line versus off the line. And if I find more browse on the line, then it makes sense that a browse subsidy is occurring. But to be extra sure that this is actually benefiting ungulates, I'm also going to be looking at the actual bite marks to be sure they're actually, the browsing activity is higher on the line than off the line as well. Okay, and because this is going to vary between, say, a peatland and an aspen forest, I'm also going to sample along an elevational gradient from upland to transitional habitat to lowland. And that way comparisons can be made between different habitat types as well. So in the end, I hope to produce a spatial model that can predict areas of high potential for browse subsidy. And that way restoration resources can be allocated to where they'll be most effective at both suppressing invasive white-tailed deer populations and thereby conserving caribou, hopefully. So this is the last slide. This is a picture of me. That's a picture of Dr. Scott Nielsen, my supervisor at the U of A. Thanks to him, thanks to BERA, thanks to you all for listening. And if you want to get excited about shrubs, come on by and check out my poster. Okay.
Okay, so I think the next session is next. So if Maria and her group, and Scott Ketcheson want to come up. Are you starting? Thank you.
Okay, great. So that was your first taste of lightning talks. And now we're going to continue right into talking about our next tactical deliverable, which is restoring natural carbon dynamics. So Greg sort of already this morning took you to the boreal forest, and I'm going to take you back there. Here's one image, and you can see some of that footprint on the landscape, but you can hopefully also see that the boreal forest in the BERA study area and across most of the boreal is really a mosaic. It's a mosaic of upland forests that are interwoven with forested peatlands, more open peatlands, wetlands, and lakes. And it's really that mosaic and the interactions between those different ecosystems working together that provide the functions that we want from the landscape. And in this case, we're really interested in climate regulating functions through carbon storage in soils and vegetation, and the provision of water resources. So we've just already talked a lot about promoting return to forest cover, and those forests, those trees are obviously a critical component of that carbon storage. But in the boreal forest, the vast majority of that carbon is stored in soils. So we're also really interested, or why our topic is called Soils and Ecohydrology, is because of the importance of those soils in returning those natural carbon dynamics and providing the water that the plants need to grow and also store carbon. So the legacy of the human footprint on the landscape likely impacts the ability of the landscape to perform those functions. But unlike some of the things we know about habitat, we know much less about what that footprint is doing for these functions. And particularly, we don't know well the cumulative impact of a variety of these disturbance types at the ecosystem and catchment scales. So our goal is really to try to start to fill those knowledge gaps so that we can start to include these types of functions in our management decisions, or at least understand how our management decisions are also impacting these functions. And that will help us to account for that
in understanding what the disturbance was, but also in designing our restoration strategies to helpfully mitigate those effects. So we're interested in that entire landscape, but you will see that a lot of our research is focused on peatlands, and this is because they're carbon storage hotspots. As I said, that carbon is largely stored in their soils, but also because they are a target often for these restoration activities, because we know that arrested succession tends to be more common in these peatland environments for a lot of the reasons you just heard about. They get compacted, they get a lot wetter, the trees just don't grow well in wetlands to begin with. So in BERA, we're focusing a lot of our carbon storage and greenhouse gas flux studies largely in those peatland ecosystems, although not exclusively. And a lot of what we learn about return to forest cover, we can also turn into carbon stock estimates. This is important from BERA. It's important, I think, from an Alberta perspective, but I also just want to highlight this is actually going to make really important contributions at the national scale. We don't know well how to account for these disturbances in our national inventory reports of greenhouse gas exchange, and we work directly with partners that can turn what we learn here in BERA into those accounting numbers. And also, peatlands are really important on the international scale. Right now, the CBD COP is going on in Montreal, talking about biodiversity, but also just in the past UNFCCC COP in Egypt, the Global Peatlands Assessment was launched. And so we're also directly linked into those international activities where this data can then loop into policy decisions. Now, one of the really important things to get this carbon back is that we need to get the hydrology right. And so that's why we also study a lot of these hydrologic parameters, or we have too many arrows on our diagram, as Greg would say. So I'm going to pass it over to Scott to talk a bit about that.
Yeah, thanks, Maria. And yeah, good morning, everyone. So we just heard a little bit about the importance of peatlands from a carbon perspective, but as Maria has indicated, they also play an important role from a water availability perspective. So we know that the boreal landscape is covered with about half wetlands, and we know that there are relationships between wetlands and the amount of water available in a catchment. So we know that watersheds that have increasing proportions of wetlands are typically associated with increasing water availability. Yet we don't really know what the influence of seismic lines are on the way that water moves through the landscape, both at a local scale, meaning at the line level, but also whether or not the influence of seismic lines is apparent at the regional scale or the watershed scale. And so that's some of the work that we're working on as a part of our soils and ecohydrology research team, is we're really focused on evaluating and understanding the influence of seismic lines on water and carbon dynamics. So what you're going to hear about in the upcoming lightning talks from our research team are some of these different components of soil properties that impact carbon cycling. And, we're going to show our process diagram in a sec with all the arrows, but, that's what our research team is really focused on, are these research priorities around soil hydrophysical properties, the local and potentially larger scale implications and influences of seismic lines, how seismic lines influence snow accumulation and melt patterns, of course, how this all relates to water availability for recolonizing vegetation, how this impacts carbon stocks in the soil and at the ecosystem level, as well as carbon fluxes through carbon dioxide and methane. So here is our soils and ecohydrology process diagram. Lots of arrows, lots of boxes, a lot of processes, a lot of variables. And really the take-home message with this process diagram is that these are really complex ecosystems and complex processes that we're trying to understand. And there are a lot of different feedbacks, and these different processes and variables are related to one another. They're interrelated, and when one thing changes, it often feeds back and relates to a series of other changes that we're trying to better understand. And so that's what our research team is really looking at, different components within this process diagram
And that's what you're about to hear from a series of students, including a PhD student, Miriam, who's really looking to understand the influence of seismic lines on the energy and water balance. So the hydroclimatic conditions present on lines. We'll also hear from a master's student, Lalia, who's looking at snow accumulation and melt patterns on the lines, as well as the soil hydrophysical properties and changes that might occur at the local line scale, and what that means for water availability for vegetation. But these soil properties are also, of course, intricately linked with the carbon cycling, and that's where I'll pass it back over to Maria to talk about some of the soil carbon cycling processes.
Thanks. So you'll also hear a recorded talk from Marissa Davies that's really pulled together a lot of the data that we've been collecting over the years on soil carbon stocks, as well as some of the hydrophysical properties, to try to start to understand, are we actually changing how much carbon is there? And if you want to hear about her poster, you're actually going to come and see me later. I'll be there. And linked to, the soils are really important, but it's the plants that are really feeding that carbon into the soil. And so Christina's going to tell you a little bit about some work she's been doing on looking at the function of those ground layer plant communities and how they may be providing carbon to the soil, and looking at it from a plant trait perspective, starting to think about maybe some ways that we could come up with indicators that we could then develop tools for remotely sensing how these carbon stocks and exchanges are changing. Nazia is going to tell you then a bit about how we are trying to start understanding better how these treatments are actually affecting carbon storage and exchange. And Percy's actually going to start us off with just, even we don't know before we treat the lines what these lines have, what impact they've had on carbon exchange. So that actually links really tightly then to Nazia's work on, well, then what happens when we treat them. So with that, I'm going to pass it over for our first lightning talk.
Thank you, Mary and Scott. Good morning, everyone. My name is Percy, and I'll be telling you how seismic lines in boreal peatlands increase methane emissions and alter peat accumulation rates. You'll be hearing about peatlands all day because they provide us so many services, including serving as long-term carbon reservoirs. Carbon storage or peat accumulation occurs when plant productivity exceeds decomposition. This is mostly the case in natural peatlands until we go poking around. And by the way, a ton of methane gas is produced from these peatlands as a byproduct. And we care about how much methane is produced because methane traps so much more heat in the environment compared to similar gases like carbon dioxide. When we go into peatlands looking for oil and gas, we clear trees and create seismic lines. What we don't understand is the overall effect of these seismic lines on the peatland functions and services they provide. So our research pretty much investigated how methane cycling and peat accumulation rates are impacted by these seismic lines when they're introduced. Our study was carried out in 3 peatlands near the town of Peace River between 2018 and 2021. We took data on methane fluxes, biomass samples, vegetation surveys, and decomposition data together with environmental information. And these were on plots, both on the seismic lines in the surrounding peatland areas. Our results are currently pointing to wetter and warmer conditions on these lines, which are ideal conditions for increasing methane production. The changes were seen in the vegetation community, and microclimatic conditions as well are reducing the ability of these lines to accumulate peat, which is pretty much concerning. The information from this research with regard to the methane data is important for accurate reporting on greenhouse gases, not just for the boreal peatlands, but for the whole country as a whole. The findings from the peat accumulation rates are very new information as well, which is important in designing restoration targets. With heightened global focus on climate change, I believe that peatlands play a great importance, and we should all be concerned about managing these peatlands. So you can swing by my poster to get more detailed information on what we found. Thank you.
Hello, everyone. My name is Christina, a first-year master's student at the University of Waterloo. My project is about assessing changes in peatland plant community functions following seismic line disturbances. As a member of the carbon cycling team, I'm working on project IN3C, plant functional trees. I'm trying to address if the plant community functions differently on the seismic lines versus in the natural areas. Also, I'm trying to answer how the newly disturbed areas are different from the recovering areas, which were disturbed 20 years ago. Previous studies have shown that the plant community composition changes following seismic line disturbance, but we don't know how the changes in composition affect the plant community functions, such as their ability to cycle nutrients or store carbon. So my goal is to assess the changes in community functions by measuring the plant functional traits, such as plant height and leaf area. Additionally, the results of my study will show how the plant communities change over 20 years following the disturbance, and to allow us to figure out if human intervention is necessary or the plant communities can recover on their own from a functional point of view. My approach is to collect plant samples from 20 study sites within a ridgeband at Kirby South. The study sites are different based on when the disturbance happened. The study includes 17 plant species, which are the dominant species on the peatlands, and some examples are shown on the right. The results will allow us better understand how the plant communities respond to human footprint disturbance, and also pay more attention to how restoring the ground layer plants affect the community functions. Thank you, and please come to see my poster to hear more about my data and results.
Hello, everyone. My name is Nazia Tabassum. I am a PhD student at the University of Waterloo, and I'm working under the supervision of Maria Strack. My research project essentially deals with the effects of seismic lines and their restoration on peatland carbon cycling. We have already seen the process diagram a lot of time, but in the context of my research, I would like to mention that my research belongs to the wider strategic goal of carbon restoration on the seismic line. And specifically, it's dealing with the methane and carbon dioxide emission from the seismic lines and the restored lines. So the implication of my research can be broadly described under the peatland management, which aims to provide us nature-based climate solutions, since the ultimate aim is to sequester more carbon into these ecosystems and also reduce the impacts of seismic line disturbance on the existing peatland carbon cycling. So within the broader area, my research has three key objectives. First of all, to estimate carbon dioxide and methane emissions from these lines, as well as from the restored lines compared to the natural peatland counterparts of these lines. And second of all, to understand and to fill the knowledge gap of the underlying factors, the ecological as well as the biogeochemical ones that's driving these emissions from these ecosystems. And last but not the least, my research also deals with the time frame of restoration and how the ages of different restored lines are actually impacting the annual total carbon budget of these peatlands. This year was the very first year of my research project, and this summer I collected my in situ measurement data from the Kirby location site, which is under the BERA study area. And my study areas can be characterized from poor fen to fen and to bog. And it's been, has been 3 specific sites. One is the mounded line, second unmounded one, the undisturbed natural sites, and the seismic line itself. So in these 4 sites, I have actually measured carbon dioxide and methane in closed chamber through a closed chamber method. And with further analysis, I would like to present my data in the poster and also the expected outcomes of my data. So I would highly request you to join me in the poster session. Thank you very much. And next, there is a video presentation by Marisa Davis, who is not physically present right now, but we can join her through her video presentation. So here it goes. Yeah, thank you.
Good afternoon. My name is Marisa Davies, and I'm a postdoctoral fellow at the University of Waterloo. In this presentation, I will outline my project within BERA 2 that aims to synthesize soil property data on and off seismic lines in northern Alberta. Soil properties are an important indicator for the success of seismic line recovery and restoration, as they are associated with water and nutrient retention that impacts vegetation growth and soil carbon stocks. This project aims to collect new and compile previously published data on 3 major soil properties at both reference and online locations across upland and lowland ecosystems of northern Alberta. These soil properties include bulk density, which tells us about the soil compaction, and water and organic matter content. This data set will provide a summarized baseline for land managers to quantitatively evaluate seismic line recovery, as well as the efficacy of restoration techniques. From the data compilation, as well as the collection and processing of soil samples from the 2022 field season, the data set in the study currently comprises of 122 sites and 755 samples. For more details on this data set and the conclusions to date, please visit my poster. You can also email me if you have any questions. If you have data, want to contribute to the project, or are interested in joining my working group, please also reach out. Thank you for listening.
Okay. Hello, everyone. My name is Lilia Weiland, and I'm a second-year master's student at the University of Calgary under the supervision of Scott Ketcheson, Greg McDermott, and Maria Strack. And my research is focused on the impact of seismic lines on hydrology. From previous research, we know that seismic lines are being compacted, and we see an increase in bulk density of soils, specifically in wetlands, but we don't really know what's going on in the upland ecosites, transitional ecosites, or with the groundwater. And so that's where my research falls into. So within the overarching BERA research goals, my research falls under the restoration of natural carbon dynamics, specifically looking at eco-hydrological conditions such as soil hydrophysical properties, the water table, snow accumulation, and relating all of these to the microtopographic conditions on the line. And the goal of my research is to relate these eco-hydrological properties to previous research that's being done on vegetation growth on similar sites. The importance of this can be seen very clearly in these 2 images. In the one on the left, we see a seismic line which is crossing a wetland zone or a riparian zone. And it's easy to see how this seismic line could potentially impact the wetland and affect downstream processes as well. We can also see that there's a change in vegetation properties where the seismic line is crossing the wetland. The less obvious changes that we don't see are occurring in the upland regions in the mineral soils and in the thin organic layer above the mineral soils. But we don't see these changes only occurring in the summertime. We also see these changes occurring in the winter. Snow is accumulating differently on seismic lines compared to the natural area, which is partially due to a lack of woody vegetation, among other factors such as incoming radiation and wind distribution. And the impact of this when the snow is melting has yet to be studied. In both seasons, the affected soil and water properties of the seismic line could explain why some lines remain in a state of arrested succession and others recover more easily. And my research aims to quantify changes to soil hydrophysical properties on seismic lines so that more targeted restoration efforts may be made to areas which are more prone to arrested succession. Thank you for listening to my talk. And if you'd like to hear more about what I'm researching, please come visit me at my posters. Thanks.
Hello, everyone. I'm Miriam, PhD student from University of Waterloo under supervision of Strack and Scott Ketcheson. My research is looking at the impact of seismic line on water balance in boreal region. But today I'd like to talk about evapotranspiration, which is an important part of my project. As you know, seismic line can affect the whole ecosystem. In terms of hydrology, it can alter water soil moisture, groundwater, precipitation, evapotranspiration, and overall water and energy balance. The whole process can also drive methane and carbon emission as well. But today, the main questions of my project would be, how does seismic line affect the evapotranspiration? To answer this question, I set up two metastations at the Kirby sub in the last summer, one on the seismic line and another on the adjacent forested area with 18-meter distance. The relevant element of each metastation for measuring weather variables can be seen in this slide. In terms of the evapotranspiration, I use weighing lysimeter techniques, which refers to the fact that the difference of mass weights on 2 consecutive sunny days can be considered as evapotranspiration. For this purpose, I set up three plots on the center for measuring evapotranspiration on the seismic line, and also 3 plots on the hammocks on the adjacent area. On the opposite side, the 3 samples for measuring evapotranspiration from the hollows. And in the next step, I'd like to measure evapotranspiration by energy balance techniques, and also I'd like to look at the impact of different treatment of seismic line and also orientation on evapotranspiration, and finally, modeling water balance. If you are interested in my result, please come and see my poster. Thank you.
And I think we get to throw it back to Greg for instructions.
All right, thank you, Maria. Nice job, everyone. So yeah, we're about to release you into the poster session. I know we've taken up a little bit more time here than we anticipated, but we're still gonna want to call you back at 12:20 because I don't want to eat into lunch. So hopefully you've got some targets. You're now gonna go find your speed date partners out here in the atrium. We have some homework for you though. You don't just get to go and have some fun. While you're out there interacting with the researchers, speaking amongst each other, I want you to consider 3 questions. What new connections did you discover? Could be people connections between ideas or whatever. What stood out to you as a key advancement or what surprised you? And what gaps have you seen in the research presented so far here today? So you'll notice there's some colors there out there in the atrium. There's going to be some little sticky notes with the same colors. Is that correct, Matthew? Am I doing this right? It's all good. Please write down your comments on there. And I also believe that there's some boards where you can place your comments once you have them. We're going to be grading them. If you don't get a good grade, you have to take home a poinsettia at the end of the day. And if you want to get a top grade, we want to encourage you, if your comment is related to a specific project, then write down that project code so we can relate it to a specific project if you need to. Okay, with that, I'm going to release you into the wild and we'll call you back at about 11. We'll call you back